Hi, I'm Ron Majors, Senior Scientist at Agilent, working with the Chemistries and Supplies Group.
And I'm Mike Woodman, an applications chemist working with Agilent Instrumentation.
We've created a series of videos to take you through some of the top issues we see chromatographers struggling with on a daily basis. This is clearly a very broad subject for discussion, and that's why you see so many different troubleshooting guides and articles out there on this subject. Our goal here is to cover some of the top issues, and we're using video so we can visually demonstrate as much as we can.
It's a big topic, that's for sure.
Yes, generally we can look at troubleshooting issues in three ways. An issue with instrumentation, such as wear and tear on parts, contamination in the system, for example. We can look at the LC troubleshooting from the standpoint of columns. Is the column the right one for the sample at hand? In the case of gradients, has it been equilibrated correctly? And we can look at troubleshooting from method development viewpoint. Are your conditions correct? Have you modified your flow rate to account for a change in column dimension and so forth?
When it comes to troubleshooting, 90% of the issue comes down to understanding how to identify where the issue is coming from, attaching a symptom to the actual source. Often, we get chromatographers who call with a symptom and they want us to help with a solution. My peak shapes are terrible, for example. Our technical support people can only begin to help them by asking a lot of questions designed to help exclude potential sources and understand enough to be able to determine whether they need to be thinking about the instrument, the column, or the method.
So Mike, where do we start?
Well, one principle to remember is that we can only know if something is wrong if we know what it looks like when it's right. So here's one tip I'd like to point out from an instrumentation point of view. Let's take a look at the system here, an Agilent 1290 Infinity LC. The system consists of a pump, an auto sampler or injector, the column, the detector, and the data system or integrator. All of these components can develop problems and require troubleshooting. It's a good idea to have a system map from when your system was working correctly or when it was first installed. Basically, you should sketch the setup and record where your connections are, how the electrical connections were made, your hydraulic or liquid connections, and even how your modules are stacked. Understanding what is normal is one of the key things you need to know in order to identify what is not normal. Having this system map will help you do this. There is a series of questions you should ask yourself if your system suddenly begins to behave differently. Did someone else use it? Was it serviced recently? Did you change to a new vendor for your reagents? These may be clues to your trouble.
From a columns perspective, here's a good practice we recommend to help you evaluate your column performance. Run a test chromatogram using your own column right out of the box. Start by looking at your test chromatogram that comes with your column. You could get these test components, which are easily found in chemical catalogs, and run them on your instrument with your new column to compare. That will help you identify if you have any system issues that are keeping you from getting optimum results. Some people prefer to use their own sample or a standard because the test mix may not be relevant to their applications. Or you can run a test on the method you're typically running and keep that in your logbook. It's best to use isocratic conditions because sometimes a gradient may fool you into thinking your column is okay. To the point that Mike just made, knowing what is good will help you identify when you have an issue. Over time, comparing your chromatograms to the original chromatogram will help you to evaluate whether your column has lost efficiency. A loss in efficiency will affect performance in a number of ways. Also, as you expose your column to different mobile phases, buffers, samples, they will affect your column's retention in subtle ways. This comparison chromatogram will help you to identify how dramatic that change is. Also, always record your system back pressure, since a change in pressure is one of the first indications that something may be going wrong. By understanding your column's efficiency and selectivity, you can begin to isolate a potential source of problems.
So, a system map and a benchmark chromatogram are two useful tools for you to use to help you with your ongoing chromatography. It's a good idea to store these in a logbook with maintenance records for your HPLC.
Yes, you'll ultimately want to isolate your issue, if you can, to one of the following areas. System back pressure. Is it too high, too low, or erratic? Changes in chromatographic resolution, specifically retention time, selectivity, or efficiency. Problems with peak shapes, ghost peaks, tailing peaks, split peaks, fronting peaks. Baseline noise or baseline drift. Often this is associated with gradient methods or detector problems.
And you'll want to consider these problems in the context of whether they happen suddenly or gradually over time. That is also an important clue to where the problem may be originating. By keeping careful records in a logbook, you may be able to diagnose the problem faster. Another important troubleshooting tool you have on newer systems is the pressure trace data. You can use this to go back and look at your system's pressure signature. This will help you to identify or eliminate the injector or the pump as a possible source of trouble. Here's what I mean. Look at this chromatogram from a 1290 Infinity LC. It's a great example of perfect chromatography. Here, we have 5 overlays, but they are so identical as to look like one run. Clearly, this is an example of what good looks like. But recently, I began to get this result. I was able to go in and look at the system's pressure trace and see that the pressure at the starting point of each run was different. As it turns out, there was a slight leak in the injector. Not enough to present any obvious problem, but one that causes these changes in retention. If I hadn't checked my pressure trace, I might have spent a lot of time looking at other potential sources before I figured this out.
That's really a great example, Mike.
Thanks, Ron.
There's one more thing I'd like to point out. If you're watching this video on Agilent.com, you'll be viewing it in a special player we have constructed to help you get the most from the content. On the right side, you'll see an outline of each segment. You can use your mouse to jump around to adjust the selection you're interested in. Also, we've included notes in the lower part of the player to accompany the video. Some people find these notes very helpful to remember key points. Ultimately, you can select the Download Notes button on the video to get a printed copy of all chromatograms and images we've discussed, along with the notes, so you can always refer back to them.
So I think that covers the introduction. Let's move on to our first LC troubleshooting topic, system pressure changes. These various segments will feature different Agilent scientists working with Ron or me to talk through the various topics. Look for more videos in the future.